water. Today's presentation: helium in the solar system. Physicist thoughts. Let's begin.
The clouds are forming. She comes
Hope you're having a great
again. I'll go and walk with her along.
There have been some reports that there is at the moment a large amount of helium in the solar system. Large clouds of dust that have been observed have therefore been reported to be mainly made up of helium. In this article, I discussed the likelihood of that, where it may actually be coming from. Now, figure 1 below shows an image taken of what I believe is the brown dwarf binary system that has been draining our sun of its energy. Excuse me. The image was obtained from the Cosmic Artifact Research website below, www.cosmicartifactresearch.com. CJ has his material very well defined, clean, easily obtainable, easily watchable, and puts all of his mathematics, sky work, telescope work online so it's clear. And he has his own YouTube channel as well. The website contains many other such amazing images of strange objects in close enough proximity, to our sun to be photographed from the Earth's surface. As follows: Figure 1, image of a binary star system. The large amount of ionized material around the larger star makes this star very likely to be a brown dwarf star and its smaller companion of comparable brightness. It is very likely to be a brown dwarf star as well. Figure 2, hydrogen emission, iron emission. I've never looked at this document until right now. Figure 2, emission spectrum of hydrogen and iron, with 4 lines in the hydrogen spectrum and many lines in the iron spectrum spread out all over the visible wavelengths. Now, brown dwarf stars are made up of mainly iron, but they do absorb material in the solar wind of other stars, and also ionize this material, producing heat, and eventually start fusing some of the absorbed material on their surfaces. Iron can be ionized, but it cannot release energy under fusion reactions. However, as long as our sun still has plenty of hydrogen to burn, its solar wind will be mostly made up of hydrogen, and so the brown dwarfs that have come close to the sun will be able to absorb this hydrogen, ionize it, and fuse some of it to helium, and thus be able to emit a lot more light than it would if it was not able to fuse the hydrogen. Let me make a comment. I've never looked at this document. Remember how I've said let the evidence go ahead and speak for itself and lead us through this journey? Why are there big old clouds of helium? Maybe they're natural forming. I may not have done any research in that regard up until now, so I don't know anything else to compare it to. I find it an extremely interesting aspect of this research. Let's continue. Now, ionized hydrogen has a certain color associated to it that comes from the emission spectrum of hydrogen, shown in figure 2 below. Or, excuse me, figure 2 above. Okay, now I understand what we're looking at. Okay. The emission spectrum of hydrogen contains 4 lines in the visible spectrum, light detected by the human eye. Okay. Obviously. There's one red line, a light blue line, a dark blue line, and a violet line. Each line is responsible for a transition of the electron in the hydrogen atom from one energy level to another, which also releases a photon of the exact wavelength associated with it, with each of the colors in the emission spectrum. Red light has a wavelength of between 650 nanometers and 750 nanometers. The red line in the hydrogen emission spectrum has a wavelength of 656 nanometers. Now, when we combine the colors Of all 4 lines in the hydrogen spectrum, we get a reddish purple color, which is shown in figure 3. Boy, that's sure a familiar color, isn't it? Figure 3, ionized hydrogen gas glows in a reddish purple color, which is a combination of its 4 emission lines. Totally makes sense. Okay, on the other hand, the iron emission spectrum shown below the hydrogen emission spectrum in figure 2 has many lines spread out over a whole range of the visible spectrum. But there are more blue lines than any other color, so ionized iron should glow blue. However, we should not confuse iron in this plasma state with the iron that seems to have entered our atmosphere from space. Okay, all right. That's kind of what I was referring to earlier. That helium, and in this instance, iron, in its natural state, I had never looked at anything previously, so in nature, there's probably naturally occurring iron and helium. That's what I was trying to say. Okay. However, we should not confuse iron in the plasma state with the iron that seems to have entered our atmosphere from space. When not in its hot ionized state and after entering our atmosphere, the iron would combine with oxygen, and we would therefore get iron oxide, or rust. Iron oxide dust. That's probably lethal to us. Like I said, I've never looked at this material before. The impressions that I have during the video, I'd like to capture live because I'm trying to teach you something on a totally different level. If you have eyes to see and ears to hear. And I never even understood what that scripture meant until now. Oh, that's really weird, dude. Rust. If we're breathing in iron oxide dust from these objects when they come in close to Earth's proximity, we're going to have gas masks. I mean, oxygen breathing apparatus. Okay. I digress. Let's repeat. When not in its hot ionized state and after entering our atmosphere, the iron would combine with oxygen and we would therefore get iron oxide or rust, which would look red and make our atmosphere look red. That's exactly what I was getting at earlier because of the familiarity of this color. CJ has tons of really wonderful pictures of Venus too. Venus looks all kinds of weird. But maybe it's not Venus. Maybe it's the flying cheese sandwich. Whatever. They're just awesome. Okay? And I don't know what's making Venus heat up and freak out. That's why I've told people to hang out and watch out about Venus. Keep an eye on Venus. Figure 4, star in figure 2, side by side with a hydrogen and a discharge tube, glowing reddish purple. Comparing the two reveals that the color around the white center of the star is made up of some purple, associated with the presence of hydrogen, but there is also quite a bit of yellow and red, and even some green, further out from the surface. Figure 5. Ionized helium glows yellow and red or orange. Now, the colors of the outside portion of the star, which I believe is a brown dwarf, is mainly a combination of purple and yellowish red, with some green present as well. So this suggests that the star is ionizing hydrogen in combination with other elements. So we should see signatures of those other elements within the solar system in large quantities as far as I'm concerned. If with what we're used to, we're not used to those large amounts of gases and elements outside of them occurring naturally in nature because of whatever orbits we have with these different planetary bodies over time. This suggests that the star is ionizing hydrogen in combination with other elements. Helium is probably one of those elements because its emission spectrum contains a strong yellow line. In addition to red, blue and violet lines as shown on the left of figure 5. This actually causes, ionized helium glow colors to be yellow and red, and often the hotter part is yellow and the glow around it is orange or red, is shown on the right of figure 5. The green color is usually associated with the presence of nitrogen. Another reason why helium is likely to be present is that there's some helium in our sun's solar wind. Okay, that's cool. However, the solar wind is only 8% helium, and the amount of red in the ionized material suggests that there may be more than that around the star. Okay. Of course, some will come from fusing hydrogen into helium, but this is unlikely to account for all of that helium in the ionized clouds surrounding the star. So, I have a couple of videos where you see this huge diagonal cloud. And I'm not talking helium. I'm talking about ionized iron oxide dust. Let's proceed. All right. Again, of course, some will come from fusing hydrogen into helium, but this is unlikely to account for all the helium in the ionized clouds surrounding the star. So where would the extra helium come from? Well, if our sun was to run low on hydrogen for fusion reactions, it would have to start using helium. This would cause our star to heat up because helium fusion reactions have to happen at a higher temperature than hydrogen fusion reactions. Okay. Also, our star would increase in size. And would it turn redder in color? It would get big. Yeah, essentially it would start turning into a red giant. Whoa, dude. This would obviously have devastating consequences for our planet, as the sun would then heat up far more than usual. Since this has not happened. Okay. It is not likely that our sun has run low on hydrogen yet. Okay. Sorry for the slight freak out. However, we know that the brown dwarf binary system has not been close to our sun for long, so it probably belongs to another system. The system may well have a red giant star in it that's using helium as its primary fuel, in which case the solar wind from this red giant star would mainly be made up of helium, which then would be absorbed by the brown dwarf binary system. Interesting how this is all potentially interrelated. This would also explain that there may be some such helium filling this portion of space. This red giant may even be the central star in the system. Okay. As I have written before, there is some likelihood that our sun is actually part of this system, and a binary star system. By the way, NASA has a binary research institute. Has a large elliptical orbit around the central star and is now close to its perihelion position, which has brought it close to the central star and close to the other stars that may orbit the central star in more circular orbits. And since space close to the central star would be filled with the helium from the central star's solar wind, our solar system would also fill up with clouds of helium at this time. Thanks again, Chris Potter of Physicist Thoughts. Have a great day.